now that we have the code for jump search, let's ask ourselves a question. How efficient is it? How many comparisons, how many operations do I need to run for different searches? In fact, a good way to answer this is to actually run the code with some live examples. So in order to sort of understand the output better, I have added a few prints in this, in this code. Basically, I print the index value in the part of the as part of the while loop. Remember, this was first pass when I'm going over the jumps. So I just keep printing the index with a separation of comma, rather with an end of comma. So I print the index, then a comma. That way all the index appears on the same line in the print. Next, I put one more print here, which says the first pass done. So, in case my first pass, which is jump values, is all done, I put a print over there. And over here in the next linear search part of it, so maybe I can put a comment over here. This is the linear search, say pass two, so second pass basically, and this was the first pass, right? So say pass one, right? So I mean, this is just for making the code clearer. So what I do is that in the second pass, I again put a print, but this time around I print, let's say, index plus kk, because that's the way this whole loop is working, right? Basically, in order to, so I'm going to just run this one so that I can call this. Now to drive this code, I am going to take a few values. So what I'm doing is to create a list, range 100, so 0 to 99. Let's take a few cases. Case number one, I'm picking up something that is right on the grid. Remember, 0, 20, 30 is in fact on the grid, and I should be able to find this. So when I run this, exactly what happens, my jumps, and the jump step was 10, by the way. I look at my, my index values. It went 0, 10, 20, 30. That is, in fact, four jumps, four comparisons made, and case number one, hence I find my search item right on the jump grid. Let's take another example. Let's say my case number two, which means, say, for example, 64. In this case, I will do 0, 10, 20, 30, 40, 50, 60, 70. So that's my first pass. First pass is done here. Now remember, post this, because I've overshot, I come back and I start doing a linear search. Remember that small optimization I said? Instead of going back all the way to 60, in fact, I'm going to 61, 62, 63, 64. I find my item. In fact, it is done. So this part is the linear search part. This was the, let's say, the jumping part. First pass done, and very, very clear what's going on, right? Let's take another example, the case number three, where let's say the value is in a certain range, say in the same range. Actually, maybe we can make it 74.5 just for sake of illustration, going in the jump of 10. So if I were to do this, you notice something interesting happens here. I go the first pass here at 80 is where the overshoot happens. So I come back, I start from 71, 72, 73, I go all the way to 79, and then I declare, look, this item is not to be found. So that's -1 here. Like I spoke in the last video, there is a possibility to do a micro optimization, let's say, because this whole thing is sorted. The moment I had crossed 74, the moment I had reached 75, in fact, I could have terminated. That will give you some incremental, let's say, benefit in average complexity. But the worst case wouldn't change, because look, I could have been searching for 79.5, for example, right? So in which case I will have to do all these anyway. Yeah. So the worst case won't change, but there could be some incremental, let's say, complexity gain, right? Let's just try another example, which is kind of the worst case here. Let's say I pick a number which is larger than the largest. Now, clearly, we could have, caught this earlier, not run anything because it's larger than the largest, but never mind. Let's see how the loop responds to this. Very interesting. It goes 0, 10, 20, all the way to 90. It finds that, look, it's not found the number there. So first pass is done, starts looking for, so because remember, the first pass got done, not because it overshot, but because 90 plus 10 was 100. I terminated the while loop. First pass was done, and then I went to 91, 92, 93 to 99. Did not find the number, and hence I responded with a -1. Now, this is clearly the worst case. You can see the number of comparisons being done are 10 over here, and then another 9 in this. Think about it. In fact, the same exact thing will happen if I were to search for 99, which is the last value in my list. Exact same sequence goes on, just that the reason for which, let's say, uh, the exact same sequence happens, and I in fact do find 99, right? Let's do one more case, kind of another trivial case. Let's say it was -99, case number 5. Remember, smaller than the smallest. I just do the very first comparison. So, even if I had done it, let's say trivially, it would have required one comparison. That's exactly what's going on here, because at the very first location, I have an overshoot. I get out of the loop and I say, okay, look, this item is not there. So I hope this is giving you an idea how many iterations it's taking. Let's try to formalize this a little bit with a little bit of mathematics, because that becomes crucial in understanding the development of the argument further, going further. So so basically, the best case scenario is still one, because we could be lucky. The very first item happens to be the item that we are searching. However, what we are most interested in is the worst case scenario. In the worst case, I make n by m plus m minus 1 jumps. Notice in my case just now, n was 100, m was 10. So basically 10 jumps in the beginning, 10 comparisons in the beginning, the first phase, and then a linear search. Worst case, I'm going to do m minus 1. So, this is basically the worst case comparisons that I'm making, given n the length of the list and m being the step size. Again, this happens in two situations. One, the value is not found in the list at all, and the value is, let's say, larger than the largest. Actually, this has to be qualified a little bit. The value is larger than the largest, so I have to go all the way to the end. And similarly, if the value is the very last value, then I will have to spend all this time, right? Now, one thing I want to highlight, that look, I have tacitly assumed that n is divisible by m, like 110. This may not be the case, but that is just kind of like an added complication. That doesn't change situations much if you really think about it, because if n is not divisible by m, basically I am in kind of like in this situation, I will have still some part of the list left, but the worst case complexity pretty much remains exactly the same. So let's not sort of obscure the insight that we are going to get by keeping it simple, which is to say that, look, there are n by m plus m minus 1 comparisons. Average case is quite, let's say, involved, because it depends. Every number has a different number of comparisons being made. For example, let's say 30. It happens to be the grid. I get this in three comparisons. 39, on the other hand, will require, well, three, in fact 4, and then plus 1, 9, right? So that will be different. So basically we have to do a more elaborate computation, but again, worst case is what we can look at. Yeah. Now, one food for thought for you. You remember that when we did our number hunt, one of the things that we did was that when we overshot, right, when we kind of, let's say, take this condition, when we overshot, some students built an algorithm where we start coming backwards, right? The algorithm we built in the class was that we started going back to this point and started sort of oscillating here in a sort of converging manner till we get to the right point. Now think about it, are those two same as a linear search that we are doing here? Why is it that we are not going backwards, right? In fact, we're going back to the last step and moving forward from there. There's a very, very good reason for it. I'll give you a small hint. Think particularly about this case. What happens in this case when we have overshot the list completely? If we were to go back, what could potentially go wrong? Happy to discuss. But I hope you're getting the idea that, look, it's n by m plus m minus 1 in the worst case. This formula is what we'll go with, and we will try to see what is the value of m that let's say minimizes this, and what are the insights that come from this. That's for the next video, but I hope you found this interesting. Look at our website www.ybyte.in, because there's a lot of material for you to learn coding, Python, algorithms in a lively, fun manner. Take care, enjoy programming.